So this one's an interesting one because it starts with the n at the beginning, which makes it a little difficult, not a set number. So again, we start with let p of n, sorry, I just changed my pen, let p of n represent proposition, represent proposition, and the proposition is what we're given. It's true for, you can't read my writing, sorry about that, p of 1 since. All right, it's true for p of 1 since. Now, when I put 1 in for the last term, it gives me a 2. So I'm going all the way up until I reach a 2. But if I put 1 in at the beginning, I'm already at a 2 with the first term. So my left-hand side is that 1 plus 1, which is 2. My right-hand side is 2 to the power of 1. And again, if I put a 1 in here, that's 2 minus 1 is 1. I'm going all the way up till I see a 1. Well, I see a 1 right at the beginning. So that's what I'm going up to. So that's a 2. So we have our left-hand side equaling our right-hand side. So we're all good. It's definitely true for p of 1. So now if it's true for p of k, for some arbitrary value of k is an integer and k is greater or equal to 1, then we would know that, and I'm going to need room, so I'm going to write it up here. We would know that k plus 1, so if this is true, then this will work. So if, oops, that's times. I'm timesing all the way to 2k, and I would get 2 to the k, 1 times 3 times all these odd numbers, note they're odd, up to 2k minus 1. That's what I'd get. All right, so what are we required to prove? We're required to prove that when I put in my k plus 1, so k plus 1 would be k plus 2, k plus 1 plus 2 would be k plus 3, and I'm timesing all the way up to, clearly I would get, I'm going to leave a bit of room, I'm going to get, if I go all the way up to here, I'm going to get a 2k plus 2 term. Now, just note that these terms are going up by 1, k plus 2, k plus 3, k plus 4. So I can also go backwards from 2k plus 2. So 2k plus 2, the one before it is 2k plus 1. And the one before that is 2k, and the one before that is 2k minus 1. But really, I just want that 2k because I need it to match the assumption. All right, so I'm required to prove that all of that equals 2 to the power of, looking at the right-hand side, k plus 1, 1 times 3 times all these odd numbers up to, so I'll do it again, up to 2. If I put k plus 1 in, I get 2k plus 2 minus 1, so 2k plus 1 will be my final term. So think about it, the term before that, there's supposed to be dots there, the term before that will be the odd number before that. So the odd number before that is not 2k, 2k is the number before it, which is even. So the next odd number before it will be 2k minus 1, something just to note. All right. So sometimes it's nice to put the term before it as well. All right, so let's have a look then at our left-hand side. So our left-hand side, we can see that, just compare it. You can see it starts at k plus 2, but this one's the proposition, the assumption starts at k plus 1. So what I can do is, and just so I don't have to write it too many times, I'm going to leave a bit of a space here. So I've got k plus 2, k plus 3, all the way to the 2k, and then I also have 2k plus 1 and 2k plus 2. Okay, now on my next line I would write, okay, so I really need that k plus 1 so it matches up the top. So what I can do is also divide by k plus 1 somewhere. Let's put it up there. This is all times of divide, so it doesn't matter where I put it. All right, so I'm also dividing by k plus 1. Okay, so let's go back to my equals here. So now you can see this whole section up to 2k is the same as our assumptive case here. So I'm going to use p of k in this step. So 2 to the power of k of 1 times 3 times all the way up to 2k minus 1. And then I've got also this extra, I'll put it in different colours, so I didn't colour code very well there, did I? So I've still got this one, so 2k plus 1. And of course this is the same as 2 lots of k plus 1s. So I can cancel the k plus 1s there, and then I've just got a times 2. Times 2. Now that 2, of course, I'll bring right up to the front, so this will be 2 to the power of k plus 1 now. And now I've got 1 times 3 times, I go all the way up to 2k minus 1. And then the next odd number is 2k plus 1. And that's what I wanted. So now that equals my right-hand side. And I'm all good. So therefore my p of k, which I didn't write when I put in, which I should have, of course, from p of k somewhere. All right, p of k implies my p of k plus 1. Therefore, my p of n is true for all n's greater or equal to 1. All right, so I hope that helps a bit.